GameSide.com. GameSide.com.
Machine code. Computers do not execute this. This is the code you type into a text editor when you want to write a computer program. Computers convert it to machine code, ones and zeros that get loaded in RAM memory. From there, the CPU loads each instruction and digital circuits execute your program. Computers execute ones and zeros. They do not execute the code that you type in. Like everything else in a computer, an executable program is simply ones and zeros. This is a breakdown of a single instruction and how the instruction bits are allocated. A small computer program may be hundreds of machine code instructions. A large program may be millions of instructions. Above is a generic 16-bit machine code instruction. Every CPU is different. Each CPU has its own instruction size and format. Using a generic example allows us to study how binary code executes without the details needed for a specific CPU. We're going to break the instruction down into three parts. There is a 4-bit opcode, or operation code, a 6-bit operand 1, and another 6-bit operand 2. Totaled together, it's a 16-bit machine code instruction. The opcode is short for operation code. Each command the CPU executes has its own bit pattern. Add could be 0101, load 0001, store 0010. When the CPU sees this bit pattern in the opcode portion of the instruction, it executes an add, load, or store command. Digital circuits in the CPU's control unit examine these bits and send signals to the rest of the CPU to perform the task. Example, add will signal the ALU to do the addition. The size and number of operands is not only different between CPUs, but may also be different between instructions in the same CPU. The bits may be a value or a memory address. RISC, or reduced instruction set computers, tend to have 0 or 1 operands per instruction. CISC, or complex instruction set computers, may have up to 3 operands per instruction. The operand is the data used to perform the opcode's task. In case you do not know, operands are the arguments to an instruction. Look at this line of code. X equals y plus 4. The 6 bits in operand 1 may be the address of y. The 6 bits for operand 2 may be the value of 4, 000100. The operands are the values needed to perform the operation. Binary addition needs 2 operands, a left operand and a right operand. That's what would go in these two portions of the instruction. Executable commands need input. An operand to the add command could be the address or register number with the value to add, or it could be the value itself. Inside the CPU, there is a very important special purpose register named the instruction register, or IR. During execution, each instruction is loaded into the IR before it executes. Here is the von Neumann Instruction Cycle. Repeatedly load and execute instructions. Start with a fetch of the instruction and load it into the 16-bit IR. Increment the PC by 2 because each instruction is 2 bytes of memory. Execute the instruction in the IR. Repeat until you see the stop instruction. The von Neumann Instruction Cycle is a loop. You keep repeating it until the stop command is executed. The instruction is pulled or fetched from RAM into the IR. The CPU looks at the opcode, 0101, which is hex 5, and uses the operand, 101010, which is hex 2A, and operand 2, 000100, which is hex 4, to execute the instruction. We're doing the first step in the von Neumann instruction cycle. Pull an instruction or fetch an instruction into the IR. The next instruction is pulled from RAM into the IR. The CPU looks at the opcode 0001, which is hex 1, and uses operand 1, 111110, which is hex 3E, and operand 2, 011100, which is hex 1C, to execute the instruction. In this example, I'm just repeatedly fetching instructions and showing you how the CPU works, because that's what the von Neumann instruction cycle says to do. Repeatedly pull an instruction into the instruction register and execute it. The next instruction is pulled from RAM into the IR. The CPU looks at the opcode, which is all zeros, hex 0, and uses operand 1, which is all zeros, and operand 2, which is all zeros, to execute the instruction. If 0000 is the opcode for the stop instruction, the cycle ends. There is an instruction in a computer program that says stop executing. If all zeros is that instruction, we will exit the von Neumann instruction cycle. Let's trace the von Neumann instruction cycle step by step and see how the CPU executes a computer program. Inside the CPU, the next very important special purpose register is named the program counter, or PC. It contains the address of the next instruction in RAM, address 0 in this case. The von Neumann instruction cycle says repeatedly load and execute instructions. Well, where is the instruction loaded from? It's loaded from the memory address that the program counter points to. If this is filled with zeros, the next instruction is address 0 in RAM. The fetch part of the instruction cycle says go to the RAM address in the PC, grab 2 bytes of memory, and put it in the IR. So go to address 0, grab these 2 bytes of memory, and load it into the 16-bit IR. Increment the PC by 2. 2 bytes equals 1 16-bit instruction. May seem odd to increment before execute, but there is a good reason. The call command needs the new address in the PC to push it on the stack before it executes. We're going to add 2 to the program counter before we execute the instruction in the instruction register. So we'll point the PC to address 2. Time to execute the instruction in the IR. The 4 bits in the IR that are the opcode are examined by a digital circuit. Let's say the load command is 0001, then the simple circuit of A0, B0, C0, D can output a signal to execute a load command. That's how the CPU executes an instruction. It examines the 4 bits of the opcode and decides to signal what to do. The process repeats as long as the command that was just executed is not the stop command. The key is the program counter, or PC. It has the new address, so the fetch will load the next instruction. We're going to repeat the von Neumann instruction cycle over and over. It's time to go back up and do another fetch. Fetch goes to the RAM address in the PC and grabs 2 bytes of memory and puts it into the IR. 2 bytes equals 1 16-bit instruction. Note the PC is displaying binary 2, 0010. The address in RAM to the right is hex 2. We are loading address 2 because there is a binary 2 in the PC. So the 2 bytes at address 2 and 3 are loaded into the 16-bit IR. Increment the PC by 2. 2 bytes equals 1 16-bit instruction. Binary 100 is decimal 4 or hex 4. Remember to increment the PC before the current instruction is executed. We add 2 to the program counter. 2 becomes 4, and the program counter is now looking at address 4 in computer memory. Execute the instruction in the IR. The 4 bits in the IR that are the opcode are examined by a digital circuit. 0101 is in the IR in the first 4 bits. Execute the instruction in the IR. The 4 bits in the IR that are the opcode are examined by a digital circuit. Here are the 4 bits, 0101. Let's say the add command is 0101. The simple not A, B, not C, and D circuit can output a signal to execute an add and tell the ALU to do binary addition. Repeat until the stop instruction. The process repeats as long as the command that was just executed is not the stop command. The key, once again, is the program counter or PC. It has a new address, so the fetch will load the next instruction. See that 0100? We should load address 4 next into the IR. Fetch the instruction and load it into the 16-bit IR. Fetch goes to RAM address in the PC, grabs 2 bytes of memory and puts it in the IR. 2 bytes equals 16 bits. Note the PC is displaying binary 4, 0100. The address in RAM on the right is hex 4. This 4 here says go to address 4 in RAM and load the 16 bits into the IR. 2 bytes equals 16 bits. Increment the PC by 2. 2 bytes equals one 16-bit instruction. Binary 0110 is decimal 6 or hex 6. Remember to increment the PC before the current instruction is executed. Execute the instruction in the IR. Execute the instruction specified by this opcode right there. The 4 bits in the IR that are the opcode are examined by a digital circuit. Let's say the stop command is 0000. Then the simple circuit A naught and B naught and C naught and D naught can output the signal to execute a stop and leave the von Neumann cycle. The stop command, when it's executed, tells the CPU to stop executing the program. See that arrow right there? I'm going to leave the loop. Reading binary code is a very, very difficult task. A mnemonic is an abbreviation or word used to represent an opcode. Reading binary is difficult. Mnemonics help a lot. Rather than memorizing 0001 is the load command, we use the mnemonic load to specify it. When you're looking at a dump of a binary program, it is helpful when that dump uses mnemonics instead of raw binary. Mnemonics are examples of load, add, stop, call, branch, and store. All of these are mnemonics that represent certain codes. If you look at address 0001 implies that command is a load. Look at address 0101 implies it's an add command. The 4 zeros here is a stop command. 0111 at address 6 could be a call command to execute. 1001 could be a branch command. And 0010, as we've looked at before, is a store command. Mnemonics are useful ways to specify instructions. Much easier to read a mnemonic than it is to read binary data. Knowing the von Neumann cycle and the importance of the instruction register and program counter PC is critical to understanding how a CPU works.
GameSci.com